please.
Yes, and thank you for inviting me to come here. First of all, let me just give an ad for a position in the Czech Academy of Sciences in Prague on my grant to work on proof complexity or bounded arithmetic. So the deadline is the end of this month, but we're looking at maybe extending this. So if anyone's interested, please come and talk to me about it. Right. So I'm going to present basically one proof. So it'll be a bit of a technical talk, and I'll just use the whiteboard. And I'm afraid the lights aren't all working. So please tell me if I need to write bigger. So I'm going to give a follow-up to Jakob's talk, and I guess say something about one of the open problems, which is the complexity of Jakob's proof system at the end that I think he never actually gave a name to. Is that okay? Okay.
I think it's whatever is in very big.
Okay, very good. So I want to show that it has the same strength as G1, which is a system that's expected to be stronger than extended Frege, so stronger than DRAD, not formalizable in DRAD. So I don't want to get into the details of cutting planes and so on. So I'm going to give a slightly different presentation of the main rule of the system, this dominance-based rule. So here is more or less a proof system. And I'm going to claim this is the same as Jakob's system. So you're working essentially with extended Frege, or extended resolution or circuit Frege. So we're dealing with sets of clauses or sets of formulas, and we can think of these as polynomial size describing a circuit. And you're refuting things, say. So you have some set of clauses you want to refute, and you can use the rules of extended Frege. That's one thing you can do in this system. But also you can use the following kind of rule. Suppose you've, well, it's a configurational system like Jakob was describing. So you're working on some set of formulas that it gets bigger and smaller. Suppose you arrive at some set of formulas in variables x. So this is meant to be some set of propositional formulas, and this is just a vector of formulas. It's not a negation. So you've derived gamma, and then you also write down a set of extension axioms. So these are defining some new variables z from x. So this is the kind of thing you can do in extended Frege, and you can also think of it as you have a circuit that takes variables x as inputs and outputs some variable z, and delta is just a description of the circuit. And suppose you also write down a substitution, which for the purposes of this talk is going to mean a map from variables to variables. And this substitution takes x variables and replaces them with some other variables, maybe from x or maybe from z. And in general, it could also do, it could also set some of them to 0 or 1. So we have these three things, and we also have as a kind of auxiliary proof written down on a piece of paper on the side. We have a proof that gamma and delta together prove this thing. So this is gamma under the restriction omega, and this says that x under the restriction omega is less than x. So x under the restriction omega means we just apply this this substitution. So we look at each variable and we maybe leave it the same, or maybe replace it with a different variable from z, depending on what omega says. So this changes x into a different tuple of variables. And then we're saying that lexicographically, this is less than this. So maybe x is written down as x1 up to xn. And after the substitution, we have z1 up to zn. And this is saying, if you think of these as binary strings, then lexicographically, the string on the left is less than the string on the right. So this is, you can write this as some kind of formula of depth 2 or 3 talking about the variables, and it's not a fancy thing. So this is what Jakob, for example, was doing through this function x1 plus 2x2 plus 4x3 and so on. Here we're just assuming we have some formula that defines lexicographic order. So if we have these three things, then we can conclude that the set we wrote down was actually unsatisfiable. So if we've derived gamma and we have this, then we're able to finish the proof at this point. So this is a proof system. It's the similar rule Jakob had wasn't for finishing the proof straight away. It was for deriving a new clause C, but I don't really need that. So I'm not doing the C here. I'm just stopping the proof. So,
So Neil, to clarify, the substitution is really an arbitrary substitution, or because the way you said it, it sounded as if X has to go to itself or to some other, to some Z.
It's an arbitrary substitution. So we just write down some substitution.
For Z1 to be that's the next one, let's say.
Sorry?
So now you go from the X's to the Z's, possibly. So you want it for every value of the Z should be smaller?
The Z's are defined from X's. So.
I'm saying there's a formula like left, x, y. This is some extended Frege formula defining lexicographic ordering. And I'm saying if we do the substitution, then this is provable.
So does it mean that in particular, the length of the string that you get the substitution is at most the length of the original?
Yes, but I mean, we just substitute. The substitution is just something that affects single variables. So we're taking a tuple of n variables, and just for each variable, we're applying omega to it. So the issue with the system is how much logic do you need to prove soundness of this rule? So a kind of semi-formal proof of soundness looks like this. So I want to show that gamma actually is unsatisfiable in this circumstance. So let alpha be the least assignment such that alpha satisfies gamma. So here I mean alpha is an assignment to x variables, and least just means lexicographically least. This is the ordering we're always using. Sorry, we assume that that gamma is satisfiable, then we take this. And then we extend alpha to alpha together with beta, such that alpha together with beta satisfies gamma and delta. So alpha was an assignment to x variables. Delta is extension axioms defining some z variables. So beta is an assignment to z variables. So this is to x and this is to z. So this is just, we think of delta as a circuit, and we just run the circuit on alpha. We get what z is, and we write it down as beta. Then by this condition, we have that alpha together with beta, yes? Because it's just extension axioms. So all delta is doing is saying how each z variable is defined in terms of x variables. So we just do all these things to get z.
As a circuit, really.
Yeah. Yes. So it's a circuit computing the values of z. We do the circuit. We get beta. So we get that alpha together with beta satisfies this thing. So I'm just repeating the last thing in Jakob's doctrine. Now, if you look at this, we let alpha prime. So this is an assignment to x and z variables. We let alpha prime be this thing composed with omega. So omega tells us how to assign x variables if we know how to assign x and z variables. So given any x variable, we change it into a different variable, we evaluate it here. So this gives us a new assignment to x variables. And then just working through the definition of restriction, as Jakob said, we get that alpha prime satisfies gamma. So this is just the meaning of this. So if alpha together with beta satisfies gamma under the substitution, that's the same as taking out this, applying the substitution, it satisfies gamma. And alpha prime is lexicographically less than alpha. So you can think of this, this alpha, say, as binary strings giving values to x variables, beta is to z variables. And then this lets us produce a new string for the x variables. It satisfies gamma by this, and it's less than the one we started with by this. This is now a contradiction by our choice of alpha. So this is why it's sound. The same proof, well, similar proof to what Jakob gave, and you can kind of see that if we wanted to do something such as, sorry, Jakob.
Yeah. So once you have this circuit that defines your new variables, this is maybe connected to, was it Albert, like omega, could I think of z as being like x1 prime up to xn prime, and without restriction, just let omega map xi prime to xi without the prime, because the circuit will do the rest for me.
I think I don't understand. I mean, this is fairly flexible, so you could copy all the x's across as well if you wanted. But you mean just sort of work out in advance what the new values are going to be?
No, I mean, I don't need a general omega. I could just say that omega sends, like I identify which set variable carries the new variable for my next variable. So that omega is just basically projecting.
Yes. So I think it'd be a consequence of what I say that basically that's what you need. So you could put more restrictions on omega, but for the full rule is
yeah. No, but I mean, yeah, I meant
the generality.
Sorry.
Without all the generality.
In the end.
And delta has like an inputs and an outputs, and that's what omega is. Nothing.
Well, I mean, this omega has 2n inputs or more. We don't know how big z is. I mean, in particular, the z's will also be working out internal nodes in these circuits, but I think I'm getting a bit far away from what the question was. Let me carry on. Yeah, so if you wanted to formalize this in bound arithmetic or at all, then the kind of business part of it is actually finding the least assignment here. So you can do this proof if you know how to find the least assignment satisfying something. And I want to show that's actually essential in that the proof system itself effectively simulates this ability to minimize things or to locally minimize them. So let me put this in terms of proof complexity, of propositional proof complexity. So we're going to talk about some strong proof systems. So let's draw some proof systems. So a fairly weak system is resolution. And then here we have cutting planes, which I'm mentioning as it's the system Jakob is building on. And here we might have something like AC0 Frege. Both of these are weaker than Frege. And then above this, we get to extended Frege. And this is where things like Dirac live. That's equivalent to extended Frege. So if you want to show that something is stronger than extended Frege, you're not really going to be able to prove a separation, but you can prove effectively hardness results for some standard stronger systems. And there are some stronger systems. And the one most I'm going to talk about is called G1. And this can go further if I can reach it. There's G2 and so on. And what is G1? So Frege is equivalent to LK, which is the propositional sequent calculus. So one standard way to write Frege proofs is that a proof is a series of sequence, and each sequence you have some propositional formulas on the left and a sequent arrow, and then some propositional formulas on the right. And you reason with this. And this is sometimes called G0. And then G1 is the sequent calculus, but where you have slightly stronger reasoning, where you can have existential quantifiers over Boolean values. So a sequent now, rather than just having propositional formulas, you're allowed to quantify over 0 and 1 values. So this is effectively a shorthand notation for saying it's true at some possible binary value of X. So it's a compressed way of writing a more expressive thing. So a sequent in G1 looks like this. And if you're proving, we're in the world where we don't ultimately want to prove or refute these quantified formulas, we just want to prove or refute unquantified formulas. And if you look at the unquantified formulas, you can refute with it. G0 is F, G1 is up here, G2 is allowing more quantifiers, and so on. And extended Frege is actually equivalent to tree-like G1. And G1 is equivalent to tree like G2, and there's various relationships like this. And just to say something about about this case. So just to talk about one direction of this, how would you show, for example, that tree like G1 is simulated by extended Frege? So what you would do is you'd say, in G1, you're deriving sequence like this. And this is meant to mean that if everything on the left is true, then something on the right is true. And you can take a tree-like G1 proof. And when you derive this, you can inductively construct a circuit that tells you how, given X is witnessing the left, you could construct Y is witnessing the right. And you can build this up into this kind of simulation. And the other direction is harder. So,
this why it has to be tree-like? Does it work?
Not entirely, but well, I don't want to talk about it because there's not much time. So where in this picture is Jakob's system? So it's built on cutting planes, but effectively with the extension rule, it's like extended Frege plus the other rule, which is why I've written it this way. And I'm going to claim it's exactly here. Now, the thing about these G1s and GIs is they correspond tightly to bound arithmetic systems. So I can draw the kind of following picture of it. So we have G1 and we have extended Frege, which is like tree like G1. And then this is actually corresponds to bounded arithmetic S22, and this corresponds to PV. So the correspondence between PV and extended Frege is something that goes back to the definition of these classes. And it's something like this. It's PV proves that for all binary strings, something is false. So this is a PV formula. So this is some polynomial time property of X. This is true if and only if extended Frege has a short refutation of the translation of this. So I'm going to use this kind of notation. So what's going on here is this is some formula about a polynomial time property. I'm translating it here into a Boolean formula by silently picking some size, some number of bits. And then here, rather than talking about strings, here I'm talking about strings of n bits. And these are now meant to be Boolean variables for the bits of the number. And we can think of the way to turn this into a propositional formula is we think of the circuit that expresses phi on inputs of this size. And this says that we run the circuit on these Boolean variables and the answer is 1. And we have a refutation of this. So in general, we're talking about provability of for all pi b1 formulas. And from this point of view, where we can kind of silently pass between the first order case and the propositional case, EF is the same as PV. G1 is the same as S22. S22 is stronger, but if we're only interested in formulas of this kind, it's the same. And then by kind of all results in bounded arithmetic, this is the same as G12, and this is the same as PV plus an axiom that essentially says we can solve PLS problems.
Who is we?
The axiom. So formally, it's an axiom saying that for every PLS problem, it has a solution.
Isn't there an issue of uniformity, like the uniform version of the G1 and the
Yes, I do. I'm sweeping that under the carpet for today. So let's not worry about uniformity.
Sorry, Neil, you said that these are equivalent with respect to this for all this kind of form.
Ignoring issues of uniformity. Yeah. Okay. And so we already more or less saw T12 because that's what we use to prove soundness here. So now I want to kind of do the other direction to show that anything provable in this, so in G1 or from PV plus this thing, is actually doable using this in this system. And I have 5 minutes, which maybe is not enough time. So, so what is a PLS problem? So PLS problem Q x, so we have some parameter x, is a triple of a initial function, initial solution, domain, and neighborhood function, and the solutions given such a problem, if it's not the case that the initial value is in the domain, then everything is a solution. So we kind of force the initial value to be in the domain. That's the first kind of solution. Any y such that y is a solution and the neighbor of y is not, that's a solution. So I've stopped writing the x for now. And any y such that y is a solution and the neighbor of y is not strictly smaller than y. Because in a PLS problem, when you keep applying the neighbor, you're meant to get strictly smaller and smaller, lexicographically smaller strings, staying inside the solutions until you find some kind of local minimum, and that's a solution. That's how PLS is meant to work. So I'm claiming that G1 is the same as more or less extended Frege plus this rule saying that we can solve these problems. So what does that look like? So I'm going to skip at this point the details of some of these translations and argue by analogy, maybe more than I should, just to claim the next thing. So I'll just write the claim. I'll write this fact. So suppose G1 refutes, by some short refutation, some formula phi x. So here, this is some kind of circuit about some propositional values x. Then By this characterization of G1 as PV plus this, and by the relation between PV and extended Frege, we can do some translation and get the following. Then there exist EF proofs as follows. From phi x and this we can derive So what's going on here? I kind of missed out a step, which maybe I should actually write. So it's if G1 refutes phi x, that implies that extended Frege informally proves that phi x implies there exists a PLS problem with no solution. So I'm characterizing this thing as extended Frege plus the statement that every PLS problem has a solution, and I'm kind of contrapositively interpreting that as meaning that if you can refute something, it means that when it's true, this PLS problem has no solution, and this is provable in extended Frege. So you can do this, and this is formally what you end up with. So this is what it looks like to have a PLS problem with no solution. You have, if phi x is true, then you can set y to be the initial value, and y is in the solution space of the PLS problem, and this is provable. And also you can prove that there's no solution. You can prove that if y is in the solution space and z is the neighbor of y, then z is in the solution space and z is strictly smaller than y. So this is saying that sort of provably in extended Frege, we can repeatedly take neighbors, and we always stay inside the solution space, and we always get strictly smaller. So this is exactly under the assumption that phi x is true. You can iterate this problem and never reach a solution. So this is what we have, and now we can refute phi. So we finish. So here's a refutation of phi in the system. So you start with phi, and then you derive, so this is the next thing you derive. So t is some polynomial time function that gives you an initial solution. So this is like extension variables defining a new circuit. So we get this. And then we get that phi x and dx y. So this is because we know provably that if y is the initial thing, then it's in the domain. And now we've thrown away this. So we've derived this. We have some initial thing in our domain. And now I want to apply this rule. So we have phi x and dxy and my y's in extended Frege. X and z is also. So this is going to be the auxiliary proof we use here. I'm just really written down the last line there again. And we let omega be a substitution that takes x and y variables and it maps them to x, y, and z variables. And it just replaces y with z. So this is my description of the substitution omega. And then now look at the structure of this. So we'll take these two formulas here, and we'll call them gamma. This thing is just defining some new variables from old variables. I should really have written lines over these. But so this is delta, this is extension axioms. And then this thing is now the same as gamma, but we just replaced y's with z's. So this is gamma restricted by omega. And this thing is saying that, again, this is just, well, y restricted by omega is less than y. So y was one of the, together the x's and y's form what I call the x variables here. And our ordering, we only cared about the y part, we didn't care about the x part. So I'm claiming that this proof is exactly the witness we need here. So by our rule, we can now derive a contradiction from what we've got. And so this is how we've proved, we've simulated G1 by this dominant system. And I'll stop.
The other direction simulation is just by proving reflection of the system.
Yes, so it's just because to do the proof of reflection, you just have to take the minimum. The T12 does it.
So in particular, in this kind of proof, it's enough to apply the rule only once.
Yes. Well, this is still a work in progress. It's not completely written out. I think you actually only do once, but probably have to appeal to the robustness of the bounded arithmetic somehow to get that.
Okay, I think. Thank you.